Okay, so welcome back, and today we've got a new topic, and today we will be studying cooperation. So a lot of good things happen in life because I cooperate with you people and you people cooperate. A lot of you people are passing the course because you're cooperating with each other and you're able to operate in this world. You get all the food on time because your parents cooperate with you, and your house is nice and tidy because you cooperate with your parents. So you listen to them and solve their problems. They listen to you, solve your problems. They're nice to you, you're nice to them. We all are nice to each other. That's cooperation. And just imagine if you were alone in this world, you were supposed to do everything. Work for yourself, grow your own food, cook your own food, clean your own stuff, build your own house. Wouldn't have been possible. So, human existence is only and only possible because we all nicely cooperate with each other. We play as one big team and we make sure that we help each others. We help someone, some other people help us. That's cooperation. We look at cooperation in and one and only one perspective, which is evolution. So today we are studying cooperative evolution. So let's take in a few examples. So I need to evolve the best major project for this course, and it's a teamwork. So what do I need? I need great teams who make great projects. So do I make great teams by ranking all of you people up, rank number one with rank number two, with rank number three, with rank number four, with rank number five? Absolutely no, because for a great project, the top five rankers may be all developers, maybe all algorithmicians, and even as algorithmicians, they may be specialized in one particular area. So it'll be a bad project because nobody is willing to do documentation, nobody is willing to do the backend development, nobody is willing to make a cool UI. Everybody is an algorithmician, and there are only one or two algorithms in which there are five greedy algorithmicians. They all want to solve the hardest algorithm to their own credit, put it on their CV. So it's a bad team. So what will be a good team? A good team will be somebody who has one strong algorithmic developer, one person good in UI, one person good in documentation, one person who entertains all the others up and make sure nobody sleeps at night when you are making a project overnight, one person who's supposed to have a very good rapport with the professor and he'll give you the tips and the tricks of the record, and that's a great team. So evolution of a great project means having different people who are diverse and they cooperate with each other in order to make a great project. So let's say I want to evolve a great robot. So those are things that we'll be looking at in the subsequent sessions. I want to evolve a great robot. So the robot should be able to move around. It should be able to avoid obstacle, go to goal, meet the other like robots, collectively help each other in order to do stuff. So I have different behaviors, and a collection of all the behaviors makes a great robot programs. So if I want great behaviors for my robot, do I take the best behavior which is giving me the greatest score, which is say obstacle avoidance, and have different obstacle avoidance methods stacked up on top of each other? No. So I need a good collection of behaviors that together make the robot move. I want to hardware design a robot. Now, it may appear to be a completely independent problem. You need batteries, you need sensors, you need actuators and everything up. But then there's also a cooperation among the agents. I may have a design objective to be keep it cost effective. My sensor may be absolutely great, it may be too costly. All these days sensing is getting extremely cheap. As I talk, it's getting cheaper due to technology. So the sensor may be still cheap, but the problem is that my robot, I may have a design objective that it's small, and my sensor may be taking a lot of battery. And if my sensor requires a lot of battery, then I either need a bigger robot in which I can place a bulkier battery, or I operate for a very small duration of time, both of which are not a great solution. So you see, even from a hardware design perspective, the batteries, the sensors, the payload capacity, the overall robot design, the choice of actuators, they all together must cooperate to make a robot as per whatever design principles you have, to be cost effective. Maybe extremely high precision is not required, but should work for a sufficiently large time, and should of course display in the basic behavior that it is being used for. To let us say the fact that I want to evolve a solution to a machine design problem. So again, you've got different components. They must all cooperate with each other. They must be able to fit each other to get whatever overall you need to be doing. And that's what I will be doing over the exercise today. So let's say, what was the evolution problem? The evolution problem was that I had a machine design, I had a phenotype, I had a neural network design over here. So let's say that some design that I need to optimize, and optimizing this was my problem. So what we did was that the computers don't work with design, so we encoded that into some real numbers and some representation. The only representation we considered was a linear representation like this as a phenotype, the problem as we know it, a neural network, a machine, a project, and a genotype. Let's call this as X. So my problem was that I had to get the best X, which minimizes or maximizes. Maxim, we took a minimization problem. The best solution possible for this problem. This is what I was doing over here. And that's my optimization problem. Subjected to some constraints not written over here. So that's my optimization problem. Now I give it a new name because I'll be using in different kinds of terminologies. I give it a new terminology, and my new terminology is, I call this thing as an ecosystem. And I divide the entire genotype into a few parts over here, and this is what I call as the species. So this becomes species 1, this becomes species 2, and this becomes species 3. So the name is of course derived from the traditional cooperation, wherein there's an ecosystem where we all live in, and it consists of different organisms called as species. They are humans, they are tigers, now there's a coronavirus, there is a deer, there are insects, and each one of us has a specific work to do. Like my work is teaching, not that. So each one of us has a specific work to do in the ecosystem. The deer population cannot be extremely large, because if the deer population is extremely large, then the tigers will eat the excessive deers and it will make the deers into control. But then they have to be deers, because if there are no deers, the tigers will go extinct. So each one of the species keeps a check on the other one to make sure that the dynamic user equilibrium or an ecosystem is maintained. So there are symbiotic relationships between two organisms, biology basics. There are benefits that one organism derives from the other, biology basics, and that's what is the terminology that will be used over here of species and ecosystem. So I know that the different species which are over here must definitely cooperate with each other. If one species has a terrible problem, or if one part of the genotype is extremely bad, it will have repercussions on the other. Or I will encourage such systems where all the different species are living in harmony with each other. An ecosystem is not good which has all humans, the most intelligent beings. An ecosystem is good when the different species cooperate with each other, and the different species cooperate with each other to make the overall system best, rather than just one species being amazingly good, or the humans. So that's the basics that we are going to use for developing an intelligent algorithm right now, called as the cooperative evolution. So let's just take a standard optimization problem, any random equation, and let's see how will we actually solve this thing up. So I say f of x is equal to x1 square plus 10 x1 x2 plus 20 times x2 square plus 25 times x3 square x4 square plus 7 times x3 x4. So that's what my problem is. And if you observe this problem, it can actually be decomposed into two parts. So fx is basically a first part, which is just a function of x1, x2, plus a second part, which is just a function of x3 and x4. And we know what any technique will do. If I need to calculate the argmin of fx, then I will calculate the argmin of f1 plus f2, which is the first problem. So if I need to minimize this one, I need to minimize both this and this. And I'll join the two solutions and I'll get it. Now, this can be called as a problem where there are two species and both of them are independent of each other. Neither the first species needs anything from the second species, nor the second species need anything from the first species. So the two species are completely independent of each other. So the humans involved at one place, and they all themselves compete with each other, make themselves intelligent and do all the things. And somewhere in the water world, the sharks are competing between themselves and they're evolving themselves with each other. Not the humans have to do something with the sharks, not sharks have to do something with the humans. One is only on land and the other one is only on water. So these are independent species. Now, of course, I will solve them as independent problems and then join the solution because of the curse of dimensionality. So towards the end, it is a search-based solution. That means the total search space or the total search efforts are the total volume that I need to search for. So if x1, x2, x3, x4 is a number between lower bound to upper bound, if I try to solve fx, so to solve fx, the total hypervolume that I need to search is for variable x1 between a lower bound to upper bound, for variable x2 between lower bound to upper bound, for variable x3 between lower bound to upper bound, so this raised to power 4, or the total search effort is volume of this space, which is upper bound minus lower bound raised to power 4. That's what I need to solve. So that's a lot of effort. But to solve f1, x1, x2 and f2, x3, x4 separately, the volume of the first space is lower bound to upper bound for x1 and x2 plus the volume of the second space lower bound to upper bound square, and the total volume is, so this is the search space, and the total volume is upper bound minus lower bound the whole square plus upper bound minus lower bound the whole square, which means 2 times this. So this is my search space and this is my total hypervolume. So this is my search space and this is my total hypervolume. And you can see that this one is definitely significantly better than this and this one is significantly better than this, or it's well known that because of curse of dimensionality, so it's also known as curse of dimensionality, if I can break in a large problem into two problems, then solving it becomes immensely easier. It becomes immensely easier. So the decomposed problem is much better. Now the only problem is that this is a rarity. Two species not cooperating with each other, two species not needing to cooperate with each other, two independent species is actually a rarity. And practically what will happen is that you will have another term which unfortunately makes no decomposition possible. So now I cannot decompose it into any independent problem the way I had done previously. It's not possible to decompose this problem into two independent problems, which means now my problem is actually decomposed in a general way into fx is equal to sum f which only has x1, x2 plus sum f which only has x2, x3 plus sum f which has all terms. And therefore I cannot just break it up into multiple parts. So what I say is that, let me still say that I keep this thing as species 1, I keep this thing as species 2, and there are terms which are in addition. So this is where species 1 and species 2 needs to cooperate. So this is where cooperation should happen. If I just minimize this thing, but this term becomes extremely bad, it's a bad solution. If I only minimize this thing and this term becomes very bad, it's again a bad solution. So what I do is I try to evolve species 1 and species 2 because it's a complicated problem, and there are a few small interaction terms. So I decompose this problem into species 1 and species 2 with the only difference that now species 1 is not independent. It has some terms, some small terms where it cooperates with species 2, and species 2 is also not independent. It has some terms for which it cooperates with species 1, and therefore my solution should be something species 1 has to evolve in a way such that its own utility, its own goodness may or may not be optimized, may or may not be minimized. However, the utility or the goodness of the entire ecosystem has to be optimized. Similarly, species 2 itself may not be good. However, its work is to make the entire ecosystem good. And that's how I will try to evolve or try to solve this problem.